Good evening, all of you. I'm Engineer Pragit Videshekara, Secretary of Sri Lanka Association of Institution of Civil Engineers UK. First of all, I would like to welcome all of you to this webinar session. This webinar session is organized by the Sri Lanka Association of Institution of Civil Engineers UK in collaboration with the Civil Engineering Sectional Committee of Institution of Engineers Sri Lanka. I kindly invite to Engineer Kamala Gunawardana to provide introduction about our resource person. Engineer Kamala, this is time for you.
Good evening to everyone. Thank you, Engineer Pragit. I'm Kamala Gunawardana, a highway consultant and a council member of the year IESL for this year, and I chair this knowledge sharing subcommittee of Civil Engineering Sectional Committee. Actually, it is an honor for me to give this introductory note about this eminent personality, Professor Tishan Singh, who is commencing this valuable webinar under the title, The Current Crisis and Latest Technology-Based Solutions. He has chosen a very important topic at a time that our country is in a severe crisis situation and our professionals' inputs are badly required at this time. So, Professor Sanjay Singh is the chairman of the Civil Engineering Sectional Committee of the Institute of Engineers Sri Lanka. This session, professionally, he is a senior professor of the Department of Civil Engineering at the University of Moratuwa. His major expertise areas are widespread, and out of many, he has employed his skills and experiences in structural engineering, computer analysis of structures, and major decisive researches, including green technology for further research, developments, and dissemination of knowledge, etc. He has excelled on high-rise building structures with other major structure designs and constructions. Actually, it is very happy to say that he has taken the number of series from the high-rise building area for our IESL members. Further, Professor Jaisingh has extended his contributions to the sustainable built environments in locally and internationally, and his practical design and constructions of green factories, buildings with the use of many principles as applicable to built environments. So with this brief introduction and without further ado, I invite Professor Tishan Jaisingh to proceed with this webinar. Please enjoy this fruitful webinar, and I hope you will update what he gives us. Thank you.
Nire Kamala? Yes, sir.
Professor?
Nire Kamala, can you hear me now?
Yes, I can.
Yeah. Right.
I can.
Yeah, just one more.
Okay, thank you.
Good evening, everybody. Today I'm going to present about the current crisis that we are facing in Sri Lanka and the latest technology-based solutions. So basically what I'm going to do is, I'm going to first describe the problems that we are facing, the reasons of the problems. And then I'm going to tell you about the kind of research we have done at Moratuwa in the last 30 to 40 years. And then how we are going to upgrade that work or adapt that work for the latest technology. And then how we can make use of this technology to kickstart our construction industry. So that is the basic theme that I'm going to use today. So that is the background, the problem identification, crisis in the industry, construction industry, order materials, solutions and conclusions. So let's look at the reason for today's crisis. Now, if you look at today's crisis, the main problem is related to energy. So if you look at what we are short of petrol and diesel, we are short of gas, we are short of electricity, and then we also have huge number of vehicles. It's about 1 million petrol cars, but if you look at the problem, that the number of petrol cars has increased by about 500,000 from 2012. And if you look at three-wheelers, we had about 500,000 in 2012, now we have about 1.5 million. So about 1 million increase in 2000 from 2012. And then we also have about 4.5 million scooters and motorcycles, and about 2.5 million has come in the last from 2000. And we also have 1 million diesel vehicles, but very few diesel cars now. So because of that, we can say the diesel vehicles are actually doing a big service to the country because they are used for our industry, industrial applications mainly. So even the vans all are used for transportation and other activities. Then we have to look at the additional problems. So if you look at this problem, there's a huge problem created by the energy related problems. And then in the electricity sector, we have a problem because we have not done enough to promote the non-renewable sector while having enough safeguards in the non-renewable sector. So renewable sector, we have not done enough. And non-renewable sector, we have not gone ahead with the Sampur 500 megawatt plant, which was almost there to happen in 2015, but we have not gone ahead with that. So with all these problems, we have a serious problem in the energy sector. I'm not going to talk much about it because many have talked about it. And then the additional problems. So government of Sri Lanka helps all the people with free education, free health and many other subsidies. But when they grow up, when they go out of the country, either for employment or migrate, they don't select the legal means of sending money to Sri Lanka, they select illegal means. So as far as government is concerned, government always had to rely on borrowings to fund these additional expenditure, and also due to various the Euro-friendly policies that we adopted, we had to change our taxation system at the port of entry for motor vehicles and many other items, and that actually made us to go for very short-term borrowing type funding to have the dollar reserves in sufficient level. So in the last, I would say for the last 10 years, we have relied a lot on borrowings, market borrowings, rather than the project-based borrowings. And though we talk a lot about Chinese loans are only 10%, Japanese loans are 13%, and then we have other loans. But when you look at the other borrowings, about over 50% of our borrowings are short-term international bonds. So that's where our biggest problem. Our biggest problem is not the money that we have borrowed from China. It is the international bonds that have been actually floated by successive governments, especially after the end of war. So then this dollar crisis has created a new problem. That is, when we even to do manufacturing and exporting, we need to import raw materials. Now we don't have dollars to import the raw materials. So that is creating a bigger problem, and that is also causing unemployment. And then a lot of money is kept abroad by exports. That is another. They are not bringing the dollars back. They are bringing only the amount of money needed to pay salaries and also to run their industry. They are not bringing all the money they earn. They keep some of the money in abroad as well. So that's why if you look at the export sector in Sri Lanka manufactures 25% of the solid tires in the world. Solid tire demand, 25% is by Sri Lanka. And Sri Lanka is one of the biggest exporters of tea. And Sri Lanka manufactures a lot of rubber gloves. Sri Lanka manufactures a lot of sails used in the pleasure boats. So there are companies like North Sea. And then, we do many other things. We export a lot of cinnamon, we export a lot of other materials, but still we are short of people. And Sri Lanka is a country of only 22 million people, about 2 million people or more than that is living abroad. So with so many people living abroad, still we are short of dollars. So there are two reasons. One is whatever the amount of dollars we spend. Recently it was reported Sri Lanka is a country which has the highest consumption of petrol in the region. And which means, over the successive years, we have adopted wrong policies. What is the wrong policy? The wrong policy is when a kid fails in the O-level examination, the parents have no other option other than making him a three-wheeler driver. So, because in the industry or in the society, if you say I'm a mason or a carpenter, you don't have any place. But if you say I'm doing my own business, I'm running my own three-wheeler, I'm doing a bit of other business as well, then the situation is not as bad as saying that I'm a mason or a carpenter. So we have never addressed those issues. And in addition to that, when the parents look at their kids who have failed O-level, the easiest thing is spend 50,000 or 100,000, buy a three-wheeler, which is about $500,000, used to be about $500,000, and so you get a lease. So the kid suddenly becomes a three-wheeler, and he will never make any contribution to the real economy of the country. Then you will ask, how can we afford all these three-wheeler? And that is because we have about 2 million or more people living abroad. And also we have a big diaspora. And all these people are sending money. And there's nobody to do the day-to-day work at houses. So most of the day-to-day work is handled by these three-wheeler operators. So we actually created a society which you cannot find anywhere in the world. And we kept on borrowing, and suddenly we are in a crisis. And so now we have to see what are the solutions that we have to come out of the crisis. Before I come to the problems in the construction industry, I would like to tell a few things. I mean, even today, we are not doing the right thing. Now, if you look at a country in crisis, any other country in the world would start pumping a lot of money for employment generation. And some of the things that you do, that you can easily see that they do in Australia or England or America is, they kickstart many construction infrastructure projects, because they all know infrastructure projects can create employment, and creation of employment can add growth to the economy. And when there is growth in the economy, it's far easier to come out of the mess, because a lot of people will be in a positive frame of mind. But what has happened in Sri Lanka is a lot of people are in a negative frame of mind, and because of that reason, we are not doing the right thing. We have stopped all the construction, and we are thinking negative. And then I take one example and show that even today we are doing the wrong thing. Now let's take the petrol imports are restricted. So if the petrol imports are restricted, what shall we do? You might say, okay, we ration it. But I would say it's a wrong policy. What shall we do? We should look after the people who are dependent on petrol. That means we must give petrol to the three-wheelers. But what is happening today? Three-wheeler is given 4 liters of petrol, whereas motor car is given 20 liters of petrol. And if you use 20 liters of petrol in a motor car, how many employment opportunities we create? Or how many people we are going to look after? The answer is maybe none. Whereas if we give 20 liters of petrol to a three-wheeler, what will happen? That person will run his three-wheeler and earn some money and look after his family. So what we have to understand is, due to the wrong policies of successive governments, where we have never looked at the real underlying problems in the society, we have created a big mess in the society where we are having too many drivers and very little construction workers. It should have been other way around. We should have a lot of skilled people working in the country, whereas we should have a reasonable number of drivers. But today what we have is, we have a huge number of drivers, but we don't have skilled people. So now we have created a problem. Just because we are in a crisis, we can't change it upside down. So what shall we do? First thing is, let the status quo remain, and then gradually see how we can change this situation. So if you are to make sure the status quo remain, whom shall we give petrol? We should give petrol to people who are dependent on petrol for their livelihood. And we should not give too much petrol to the people who are using for their comfort. So that, we can promote people using public transport more and more, and people hiring cars more and more, but using their own transport less and less. The moment you do that, you will see a lot of people will be earning some money, and the income will be distributed. The crime rate in the country will go down, and we can make sure until the crisis is over, we have looked after majority of the people, so that many kids may not have malnutrition by the time we end the crisis. So that is the way we have to look at it. But if you look at all these QR code and what else? I mean, we have this number plate based business, rationing. They are all short-sighted policies by administrators who have never tried to understand the underlying problem in the country. So it is the same thing in construction industry. So let's see what is the problem in the construction industry. Construction industry, if you look at the days, I was born in 1963, so I'm close to 60. And I know when I was a kid, we used a lot of natural materials. We used a lot of kabuk. We used a lot of earth. We used a lot of water land for construction of houses. And those houses were not bad. They were reasonably good. They had cement rendered floors, and they looked strong because the walls were thick, but out of earth or water land. Then 1977, we started opening up the economy, and then the Prime Minister Premadasa wanted this 1 million housing program. So for all that, we suddenly decided to change. To what? We changed to burnt clay bricks, we changed to cement and concrete blocks, we changed to tiles as finishers, terrace as finishers. So we changed a lot. And with those changes, what happened? We did not look at it in the holistic way, we just changed. And that change over 30 to 40 years created huge problems in the country because we have overexploited the available natural resources over a very short period of time. And then we thought, okay, let's go for sustainable construction. And this movement all started somewhere around 2005 and then gathered momentum around 2010. By 2015, it became a marketable commodity. So the government of 2015 decided we are going to be very green. So how did they become green? They prevented people using earth. Even to move 1 cube of earth, you need a permit. I mean, they are all popular moves, but not the moves that we have taken with the correct attitude. So to move bricks, you don't need a permit, but to move a cube of earth, you need permit. So what is the result? I mean, we killed the industry that was emerging as alternative materials. So if you look at the various materials available, Sri Lanka is a tropical country and we have a lot of earth. And earth is an ideal material for construction. So we should think about, and at Moratu University, we have used earth a lot for construction. To develop earth as a construction material, we have done a lot of research, and we have done a lot of research to develop waste-based materials converted to become construction materials. So how do you use waste as a construction material? And then we also had entrepreneurs like Professor Ranjit Disanayaka who got involved in with another engineer, Nalin Pathiran, and they set up a factory. For what? To manufacture aerated autoclave blocks using the waste from Norechole plant, Norechole coal power plant. They created a big factory, and then Access also got involved later, and now they have 2 factories. So we can happily say in Sri Lanka we are converting waste materials to valuable building materials in Portland. And also then there are other entrepreneurs who thought, okay, we have a good industry at the free trade zone, and they bring a lot of machinery and materials, and some come with packaging materials. So we have huge quantity of expanded polystyrene coming into Sri Lanka, which cannot be got rid of because we cannot burn it. It's a highly poisonous material, so we can't bury it. It's a massive quantity. So he thought, okay, let's convert all these back to beads and put them into panels, and let's manufacture lightweight concrete panels in Sri Lanka. So we had many people doing everything on their own, and unfortunately we have so many government institutions who are there to promote all these research and development. It's very unfortunate to say very little support is given, even when the project is applied for, they are just shot down. For example, we applied for 35 million NRC grant to develop all these materials and make it to showcase the products, and we were not given. And it was given to a project where most of the money went to projects where very little progress could be made. So basically, what we have seen is there are so many government institutions that are there to promote all these materials, look at the policies, but they have just become places where people thought no work means no problems. If you try to do a lot of work, you are going to get a lot of problems. So basically, it has come to a level today, we have to do everything on our own, using our own money. We have to do research, and then we have to do the prototypes using our own money, and then promote the construction using our own money. So that is the level that we are in today. So because of that reason, so I thought the ideal is, let's share the knowledge as much as possible. So sometimes there may be few among us who are willing to experiment with these products so that we can come up with very good solutions. So that's why I said, let's look at the research and see what we have done in the past, and then see how those fit with modern technology. And after that, we see how we can use those technology to reduce the cost of construction while having high quality finishes, and then see whether we can match the prices of construction that prevailed before the crisis came. So if we can do a building at 2019 prices, then we don't have to stop any projects, because we had projects in 2019 where the money was allocated and banks were willing to fund, but banks are not willing to fund at today's cost, but they have already decided to fund it at 2019. So what we need is technology that will allow us to go back to those 2019 costs using value engineering solutions. So today's future will lie with value engineering solutions, but again, value engineering solutions cannot be based on automation these days, because energy is so expensive. Because energy is so expensive, we have to go for labor-intensive construction with new technology than machine-intensive construction. For example, I was doing my industrial training at Kadwela Bridge site in 1984, and we used to cast 76 feet long, 1.2 meter, 4 feet tall bridge beams at the site, and we never brought ready-mix concrete. We mixed all the concrete at site, and we used to get strengths in the range of 40 megapascal, because the target range was 30 megapascals. So we were getting, without using any admixture, we were getting strengths close to 40 megapascal at the site with site mix concrete. At the age of 28 days, we used to get that kind of strengths. So basically what we have to understand is, we have adopted modern technology without thinking whether the modern technology is actually applicable to us. That is something that happened over the last 30 to 40 years. And today you will see, we use modern technology, but associated with the modern technology is a huge usage of energy. And today the problem is energy costs have gone up by nearly 300%. Petrol used to be about 150 rupees or less. Diesel used to be around 100 rupees. Now it has gone up to 400 rupees. So the cost of energy has gone up by 400%, 300% or 400%. So anything that is energy intensive is going to cost a lot of money, whereas the labor charges have only doubled. Labor charges used to be around 2,000 to 2,500 rupees. Now today it is about 4,000 to 5,000. So which means labor prices have doubled, everything else has increased by, so labor prices have increased by 100%, whereas everything else has increased by 200 to 300 or 400%. For example, steel has increased by about 300 to 400%. I'm talking about 1 ton of steel. So when you look at all these, there's one thing clear. We have to go for new materials, we have to go for labor-intensive construction, and we have to also go for construction that needs less material. So that's the only way we can bring the costs down, so that we'll be able to tell the banks again, let's fund these projects again. We don't have to stop the projects, because our project reports that we submitted to you in 2018 and 2019 are still applicable, and what you have to give funding is only what you promise. We don't want anything extra. The moment if we can say that, then the banks will see that they can fund the construction again. So what we need is, we have to go have good policies where we look after the employment of the people rather than we look after the people of Sri Lanka. Because the moment you are looking after the employment of the people, automatically you are looking after the people. But very few people have understood this truth. We are just playing with fire without thinking too much. So we are bringing some petrol, some diesel with loans, and we are just wasting it. Rather than doing that, we must use it for income generating activities, and then we have to gradually reduce the dependence on energy for day-to-day lives. That means, we must go for public transport based things, and anything supporting public transport we should promote, and we should discourage private transportation. And then that is one of the key sector. Then on the energy side, we have to think about off-grid autonomy. And then when it comes to construction, we must again think of construction that needs less and less and less transportation. So that means, we have to think about labor-intensive site-based construction than automated construction where we rely a lot on machine. So with that is the premise that I am going to make the presentation today. So now we have some idea. So I will stop share this one, but I will start sharing another one, another presentation. Right. Now, before I go into the details, I will show you some of the research that we have done at Moratu University. So basically, earth is a very good material for construction. So I will just show you some slides of different machines that we have used and the kind of testing we have done. So we have done all kinds of testing and the kind of buildings you can construct with these earth-based materials. So you can see the nice building, we call it Nelung Art Center at Hyde Park Corner, constructed by Maga Engineering. And then we have done a lot of testing for various paints, coatings, and so on. And then you can construct, large houses like this using these materials. And then, you can also go for semi-mechanized construction like self-rising steel shutters with rammed earth. And this is a house that was constructed by using that technique without plaster. But you can easily plaster this, and then those will all look the normal house constructed, and nobody will be able to say whether we have used rammed earth or bricks or whatever. And then rammed earth can also be constructed by using plywood shutters like this. And this boundary wall is still there. And I have used a lot of rammed earth boundary walls, and they generally don't decay. We don't apply any finishers or anything. They are just like this. And they last a very long time. I mean, they become stronger and stronger and stronger with time. And then these are rammed earth house, and these are rammed earth building in Germany. And this is a 13 house project. And in this house, even the foundations are out of cement stabilized rammed earth. All these retaining walls, foundations, all are out of cement stabilized rammed earth. And then, we can also use waste material. So we create a lot of construction waste, and all the waste can be demolition waste can be crushed and converted to this kind of materials, and those can be mixed with soil, and we can cast blocks using those demolished materials. So these blocks are actually cast with building demolished construction waste, and testing was carried out, and they found you can get reasonably good results with those as well. And then, so that is all about earth. So earth can be out of rammed earth or block walls or anything you like. And even the demolished waste also can go into soil, because generally, we are relying on, once it is crushed, it can be used as an aggregate. But only thing is, you might need to use little bit of little high amount of cement. And then this is a panel that is made out of expanded polystyrene, and then we used it as it was a non-load bearing material, but we used it as a load bearing material. And then, we have done a lot of research on it, published internationally, and a lot of testing has been done with full height panels, flexural testing, and then real construction. And we constructed this particular house, and it was all funded by, fortunately, by engineer Niranjan Fernando. He funded it because he's doing he's using a lot of those materials. He's manufacturing and he's running his property development in addition to doing research results. And we did finite element modeling, and then, constructed this building. And it's a display house. You can go and have a look. And even the staircases was out of those panels. And we also use this nerd system as the slab. And we did full-scale load testing. These are very expensive testing. Still, we did it because Mr. Niranjan was very helpful, and we had the support of Department of Civil Engineering. So we spent a lot of money and done a lot of research. And then we have done the prototype as well. And then we extended it to apartment buildings with research projects, because we knew once we constructed this building, load tested, we knew what we could do. So we went for these arrangements that are possible and developed all those apartment buildings where you don't need any columns. So, and then aerated concrete blocks that are manufactured in Putlam factory, and it belongs, one of the owners is Professor Anjit Disanayak of our Institution of Engineers Council member. And then I will also go for this material, that's the Dura panel, and there's a pretty strong material. You can see we are using straw to manufacture boards, and we can have sound insulation board, acoustic board, laminated board, and Dura normal board. And I use this for a lot of construction, because once you use the laminated board, you can use it as a flooring material. With laminated board on the upper side, you can use it as a ceiling material with laminated board on the lower side. And for all the other sides, we generally cover it with polythene sheet, so that even if there's any water leak or anything, nothing will happen to the Dura panel. And then I used it for very big construction in not only with Dura panels. I mean, their turnover is about 120 million rupees, or maybe 300 million rupees a year. So basically they are doing okay. They are not making, I think their turnover is about 350 to 400 million rupees every year, so that they can make a reasonable profit after making salaries to all people. And here you can see the ceiling is out of Dura panels, the walls are out of Dura panels. This is a steel building, but composite floor and tile floor. So everything is there. Only this part is out of block work, because that is the bathroom, washroom block. So that's where all the washrooms are located in this hospital building. So only that part is out of masonry. Everything else is all these renewable materials that allowed very cost effective but very fast construction. And this ceiling was completed in just in 2 days. The whole ceiling was completed in 2 days. And these walls are also like that, very fast construction. Basically, this I completed 2 of these 2-story buildings. This is upper floor, two of these two-story buildings in 1 month. So that's a very fast construction because these are concrete floors. So massive concrete floors, and the length of the building is about 50 meters, width is about 15 meters. Because I use a lot of these materials, alternative materials, I could finish it at a lower cost. Cost was only 3,500 rupees per square foot, when the normal cost was 7,000 rupees per square foot. So 50% of the cost by SD and CESC. And then we constructed 4 operating theaters, and these operating theaters are out of composite board paneling. And even today, if you go there, you will see that they are very well maintained, very well functional operating theaters with laminar flow diffusers. And these are 2 buildings completed in 1 month. And you can see the 3rd building is coming up, and then there was another building that came up somewhere. So basically, then I can show you another system that is, one of the biggest problems that we face in multi-story construction is when you want to do a 20-story building, there's a huge amount of steel required, huge amount of steel required for the floor slabs. And then you'll find that floor slab has suddenly become a very costly item because it needs a lot of concrete, which is expensive. It needs a lot of steel, again very expensive. Because we are using a lot of concrete and steel, what happens? We need a lot of labor, or we need a lot of energy. So we need to have truck mixers that will bring the concrete, and then we need a lot of materials brought to the vacuum plant. So all this means energy. And because energy is so expensive, you'll find concrete floors are very expensive. So what is the way that we can reduce cost? The only way we can reduce cost is by reducing the amount of concrete needed, by reducing the amount of steel needed. And if possible, reduce the amount of shuttering needed, so that the labor needed for making the shuttering can be reduced. The plywood boards that we use for shuttering is also very expensive these days. A plywood board can cost up to 10,000 rupees these days. So it's very expensive. So even if you reuse it, still the per square meter costs can remain high. So what is the way that we can minimize the cost of concrete slab? So the system is, we are looking for the history. What is the history? History is after Second World War, when the Second World War ended, there was a huge population boom in the world, and that population boom became a reality because the medical systems in the world developed a lot after Second World War. So the number of deaths reduced, number of infant deaths reduced drastically, and then we had the United Nations, so they also had various programs to help the world. And then America emerged as a very rich nation, though they were a poor nation. After 1929 depression, America was not doing well, but after the World War, America started doing very well. So there was a huge population boom, and associated with that was a huge construction boom. But the world manufacturing facilities were not sufficient, so steel was very expensive or short supply. So because of all that, people thought, okay, the most important thing is we must save materials. So those days, they included in the course of practice the rib slabs. The idea of the rib slab is you create a beam and support the slab so that slab can remain very thin. Then with time, materials became more and more. China also started manufacturing in big quantities, and Australia started supplying huge amount of natural resources to China. So suddenly construction materials became less expensive, labor became more expensive. So all the developed world, they went for rapid construction techniques because so that they can reduce the amount of labor need. So they went from normal solid slabs to flat slabs. They went from normal reinforced concrete to pre-stressed concrete. They did a lot of changes. And that is the time we also picked up and we thought what they do is the best. So without doing any research, we also adopted their technology. And our engineers also started telling flat slabs could be cheaper in Sri Lanka, and pre-stressing also can be cheaper. So yes, sometimes it can be true, but because we blindly followed what happened in the other countries, we missed the real crux of the matter. The real crux of the matter was, though it was cheaper in countries where the labor is so expensive to go for rapid construction, in Sri Lanka still it remained our cheap labor based construction was it would be cheaper. So what happened was we blindly followed the practices in other countries, and we went for more expensive but rapid construction. With that, we got a huge quality improvement. But what we didn't see was that we could have easily done cheaper construction by looking at innovation. So that is, I'm going to show you one of that kind of innovation. So here what we do is we cast a slab panel, and then we don't need shuttering, and then those slab panels are supported on beams. And then we test the panels separately, we test the system separately. So this is the beam slab system, it's tested separately, and then it was adopted in real structures. And so we showed that it can be adopted. Only thing is, if you don't like this to see the beams, just fix a ceiling, so that you get a flat. And so basically there are other systems developed by companies like ICC. They develop their own systems, low-cost slab systems, SBS systems. And then we also have the nerd center system, which can be constructed like this. And this is the plywood sheets suspended from this is a binding wire, and that binding wire is suspending the precast panel. And then you can complete the flow like this. And if you do it properly, if you want, you can provide some shear anchors here, and the moment you provide shear anchors, they are but even in this form, you don't get complaints, because the modified versions, there are many versions that are modified versions of this. They may have problems, but the original nerd system developed by Dr. A.N.S. Kolasinger is a perfect system. And then aerated blocks, and then even the manufacture of tiles. All these industries have lost the demand these days, but if the demand is there, those can be revived. For example, my house has this type. So I have constructed 2 houses, and both houses were having that type. And then this is another system that we are testing. So basically what you see is, in Sri Lanka, at Department of Civil Engineering, University of Morocco, we have done a lot of testing, and now the technology is around us. How can we make use of that technology to come out of the mess we are in today? So that's what I'm going to tell. I'll stop share now. I'll go for the. Now you have seen different systems. I'm going to write and show you how we can make use of all this technology. So first we look at a simple system, and that is a 2-story house. So what you get in a 2-story house? You'll get a wall, you'll get a foundation, you get walls, and generally we use masonry as infill. But can we use it for load bearing? That is the big question. Can we use it as a load bearing material? We know we use it as in. Then the next question is, do we need reinforced concrete slabs? In USA, Australia, Canada, do they use concrete? No, they use timber. So they make timber trusses, and then they use chipboard floor boards and plasterboard for ceiling. So the question is, can't we do that? And then you have the upper floor, then you have the roof, you have the roof. So create the roof, and can we cover it with zinc column sheets like this? And then lay some concrete on it and make it accessible for a person. So those are the things that we have looked at. And can we go for a taller building? And cannot we use cement stabilized earth for a foundation? And then can we have a concrete here? And cannot we give a 12 millimeter terrazzo finish?
Excuse
Yes.
me, Professor. Yeah,
Yes.
Professor, excuse me.
Yeah.
Yeah. Are you sharing the screen? We can't see.
No, oh, you can't see it. No, I'm using the camera.
See your profile picture only.
I think the
Now okay. Now okay.
Now okay.
now okay. Yeah. Sorry. So basically, what I'm asking is a question. In USA, Australia, Canada, do they have concrete floors? No. They go with for masonry like this. So I'm drawing the same figure again. So basically what we say is, let's have a truss, and then the wall, a truss. What is the advantage? Here we are having a slab which is lightweight. Here we are having a slab which is very lightweight. So because the slab is lightweight, then we have to ask, what is this? Cement stabilized rammed earth. Cement stabilized rammed earth, CSRE. And what is the strength? What is the strength of a brick wall? What is the strength? 1.5 megapascal or newtons per millimeter square. What is the strength of CSRE? Can vary between 3 to 4 newtons per millimeter square. So cannot we use cement stabilized rammed earth because it has the strength, it has double the strength of bricks that we use. Then we can start with something like 300 millimeter wall because it's soil. Then we go for 250. The next floor we go for 200. Next floor we go for 150. And all these floors are with a truss, and then we can have Dura panel with 4 millimeter cement fiber board. And then for the ceiling also, if you want, we can have a Dura panel. What happens? We get very good thermal insulation. We get very good thermal insulation. Then you'll ask, how can we use Dura panels? So these are Dura panel. 1.2 meter by 2.4 meter. Dura panel has a strength this way. So you need a support here, you need a support here, you need a support here. You need 3 supports. So if you have trusses at some spacing, cannot we create a support system like that? Yes. We add some timber, say 50 by 50 timber on it, and we create a support system. Then we can get a very robust system. Then you'll ask, how do you create a timber truss? There's a simple way of creating a timber truss. What you do is you take all the timber pieces like this, and then we fit the timber pieces like this. And how do you fit it? So these are open web girder system, open web girder. And in this open web girder, how do you get the connections done? Connections are done with zinc alum 0.7 millimeter sheets. So we create gusset plates out of zinc alum. Then we use concrete nails to connect all these. And what is the material for this? Elastonia. Elastonia is sometimes can create trouble. So what we do is we go for boron, borax treatment, and oil impregnation. So what we do is we put all this timber in a bath. We create a bath like this, and here also we put some cement stabilizer, and we put some oil and we put borax here, and we put all the timber there, and make them oil impregnated. For that you can use engine oil, used engine oil, and make it oil impregnated. Before doing any kind of oil impregnation, we'll use borax treatment as well. The moment you do that, this can last a very long period of time, and then we are actually making use of some used material for as a preservative, or basically to treat timber and to get rid of any pinhole borers that can damage the timber. And why did I say Elastonia? It has a 10-year cycle. So it grows very fast. It's kind of an invasive tree. So because it's a kind of invasive tree, it can grow on any kind of soil condition. You don't need fertile soil. You can grow on barren land, and it will grow very fast. And after 10 years, you'll find now the soil has improved so much that you can grow other trees. So what is the reason? When this tree creates food, most of the food is stored in the roots, in addition to whatever stored here, and it allows the aerobic bacteria in the soil to eat what it stores, and with that, lot of you can create a colony of microorganisms in the soil. So the soil, which used to be very bad quality, infertile soil, after 10 years of Elastonia plantation, you'll find the soil has become very fertile soil, full of microorganisms. And by the time you do harvesting, if you want, you can go for other kind of crop like a mango plantation or a jack tree plantation, whatever you like. Because the advantage of jack tree is also, jack tree will become mature only after about 35 years. So if you cut the tree, you cannot get timber. If you cut the tree early, you cannot get timber because timber is immature. If timber has no strength. If you want to get strong jack timber, then you have to cut the tree 35 years after planting, which means you can get the fruit out of jack trees all that time. But only thing that we have to do is we have to allow, if somebody can prove the jack tree is more than 25 years of age, we should allow people to cut it. And that will encourage people to grow jack trees. Today the problem is, because we have banned cutting of jack trees, people are not interested in growing. We have to encourage people to grow it so that they can provide food for 30-35 years, and then we can cut and get good timber. But Elastonia is other way around. We can have Elastonia plantation, and you'll ask why? Because we have 600,000 marginal land, acres of marginal land in Sri Lanka, which are barren, and if we start planting Elastonia on those lands, we can create a huge business. So basically, you can see we have a lot of things to be done in this country. Unfortunately, we are not even looking at those things. We are saying we are having problems rather than looking at and solving our problems, trying to solve our problems ourselves. We are just waiting for somebody else to come and solve our problems, which is not a good thing. So what I have shown is you can construct apartment buildings with about 4 floors. Same plan repeated. So if you look at if you want to have a plan, you can easily create a plan like this. And here you need some space for the staircase. And then you can enter here and you can have washrooms here. And one can be attached washroom and the other one can be common. So bedrooms, and you can have a wet kitchen here. Wet kitchen is an outdoor kitchen, and then you can have a pantry, and you can have living, dining, something like that. A simple 2-bedroom, 2-washroom, or 2.5 bedroom. That type of apartments can be created by using load-bearing walls and lightweight floors. And we are using all natural materials. We are not using bricks, blocks. We are using only soil, cement, and then the windows, doors can be out of timber or aluminium, depending on the availability. And then, we can also go for accessible roof, so that roof can be used for mounting solar panels. So then you can think of solar panels and sometimes growing other plants below the solar panels, which means off-grid autonomy. With battery storage, you can go for off-grid autonomy. So basically, there are so many things you can do in the apartment sector, apartment and housing sector. Apartment sector and housing sector, you can do a lot of things. And 1960s, 1970s, we used a lot, and 1980s, 1990s, 2000, 2010, what did we do? We used a lot of bricks, and by 2000, we were having huge problems with shortage, and we had to bring sand from Manampitia. Lot of expenditure today. Bringing sand from Manampitia can be prohibitively expensive, so we have to go for manufactured sand, and we have to also go for the dredged sand. So there are so many alternatives, but manufactured sand is picking up in a big way. So you can see again in 2020 we are going back to Earth. So what is the difference between this Earth and this Earth? This is local technology, and this is researched and well-developed technology. So the quality of this building has no difference to the quality of the building that we constructed in 1990s and 2000. Okay. The quality is the same, whereas there can be huge difference between this Earth building and this Earth. So on this side we have earth building in 1950s, 60s. Here we have an earth building 2020. Here our traditional way of doing things here, well researched at a university, leading university, and now we are presenting that technology again. There cannot be any difference of this earth building and this brick building. That is the trick, and we are again following some of the techniques that have been adopted in developed countries like America, where we do our own research and we generate our own materials like Dura panels. We grow our own timber and we go for timber trusses. Again, not the way that they have done. We have done our own way of developing timber. So what I say is, if we do research and develop our own things, then we can go a long way. Then, so basically, when you use these methods, even today, you can complete 1 square meter from 75,000 to 90,000 rupees. 1 square meter, 75,000, 90,000. If you ask anybody, they say the cost can be about 150,000 rupees per square meter. That is the cost any engineer would quote. I would say we can easily hit. Sometimes 60,000 is also possible, but I would generally, when I talk, I say 75,000 to 90,000 is quite easy. So that is about houses. Then let's look at how to kickstart the multi-story buildings. So in a building, what happens? We have a beam, we have a slab. Slab can be 170, 50 to 200 thickness. These beams can be 300 or 350 to 600. Now we don't think much, but what happens is all this concrete is cracked, doing nothing. Only this concrete is doing something. This concrete doing something. All this concrete is cracked. So 70% to 70 to 80% concrete is cracked. Then doing nothing. So why do we keep it? Now it's nothing structurally. Actually, it's a penalty. Now it's doing nothing structurally, but we have to carry it. We have to carry the cell. It's a penalty. And the penalty is that per square meter, the ultimate load is about 13 kilonewtons per meter. The ultimate load that we had used for design is about, it can vary between 10 to 15, so it's about 13 kilonewtons per meter. And because of that, what happens? The columns carry heavy weights, heavy loads on columns. So columns can have 1% to 2.2% reinforcement. But the minimum allowed is 0.4%. But it's very usual to find that we are needing about 1 to 2% reinforcement in the columns. And columns are also 30 to 40 megapascal. And steps will be about 30 megapascal. So steps will be 30 megapascal. The beams will be, columns will be 30 to 40 megapascal. Again, beams can be about 30 megapascal. So we are using natural materials, but we are hitting low strength. What is the problem associated with low strength? Flexurally, no problem. Here, not a big problem. What is the problem? Durability. So when you go for high strength materials with modern Euro codes, what do you get? You get durability. That is the most important thing, because once constructed, a normal structure might last 50 to 100 years. But this the super high strength material that we are proposing can make sure the buildings will last 100 to 300 years, because the carbonation rate is very low. So for that, we have to see what happens to concrete when we pour concrete. And what happens is, we have reinforcement, we have cover, and carbon dioxide is here. Carbon dioxide enters, and when the carbon dioxide enters, what happens to the calcium hydroxide in all these pores? Calcium hydroxide will become carbonic acid. And calcium carbonate and carbon ether can be divided into carbonic acid. So what will happen to the pH? pH, original pH is 12 to 13. It can come down to about 10 to 11, or it can be even lower. And at this high pH, this ferrous oxide layer is very stable, but when it comes to this, not stable. So what can happen? When the carbonation front reaches the reinforcement, the pH drops, reinforcement will start corrosion. So when you use 40 to 50 to 60 megapascal concrete, what happens? They are so dense, carbonation cannot come to the reinforcement easily, because they are very, very strong materials. They have no tiny pores, they are very dense materials when you go for high strength. So automatically you will get huge durability. And durability is a key to sustainability, because lead now promote shell. So what they say is, keep the shell, do the modifications, don't construct the shell, do only the finishes, so that you will get a modern building. The structure remains the same. What they say, structure remains the same, you do only the modifications, so that you can get a modern building by refurbishing an old building, where the cost of construction can be very much lower than a new building, because you don't have to worry about infrastructure is there, you have your landscaping is there. Only you might need some upgrading, but the cost can be very much lower. The cost can be about 40 to 50% lower than a new construction. So you can see the Euro codes allow us to use concrete from 25 megapascal going up to 105 megapascal. Our engineers are very, very comfortable where? They are very comfortable in this range, 25 to 30 range. And today's with the scarcity of materials, we must be operating in 40 to 50 to 60 range, and if possible 80 range. And when you talk about the concrete strength, again, you know, modern Euro codes are very good. What they say is, look at your curve, and if you can ensure it goes like this, you can have different ages. No need to worry about 28 days. You can have 90 days strength, 50 days or 108 days strength. So you can base your calculations on various other strengths, because there's no need to worry too much about 28 days strength, provided that you can show the curve can go on, keep on going. So that's why a lot of data is given in the Euro code. Not like British code, they are not worried about the age that you do various things, and you can hit. You can allow, you can show. So what is the secret behind this curve? Because if you take a modern concrete, modern cement, it goes like this. So why? And how do you get here? So the theory is this. Theory is 50 years ago, cement, today, the main ingredient C3S, 50%, today 70%. C2S is for 14 days to infinity, 25%, today 5%. C3A eliminate 8%, today also 8%. Because if you put more, concrete can crack. Tetracalcium aluminoferrites, maybe about 8 to 10%, today also 8 to 10%. So basically, what happened earlier, slow strength gain, but keep on gain. Today, no need to, you give on a few days. This today, early. But what is desirable? Desirable is running in this curve because we can keep on increasing. How to get to this curve? Possible in Sri Lanka because now we have fly ash. Today we have fly ash. Because of that, we can go on that curve. So we can mix 15% to 20% to 25% fly ash. And when you do that, you get enough strength. You get enough strength over a longer period of time with a lesser rate of gain of strength, which means heat of hydration is lower here, heat of hydration is higher here, and we know there's a big problem in concrete. When the temperature of concrete exceeds 70 degrees, you can get delayed ettringite formation where the C3 reaction will reverse, this will reverse, and later it will again happen. When the problem with this reaction of C3A is, if you use this amount, the byproduct is this bigger. So if it's okay to form C3A initially because of the evaporation of water, concrete is shrinking. C3A has a higher volume, the shrinkage can be reduced. So it's beneficial. When cement is immature, it's still gaining, it has no strength, then all these extra volume can be accommodated, compensated with shrinkage. But if you try to do it later, now nobody is willing to expand because it's all hard. Then it can form cracks, and very severe cracks were formed in Southern Highway because the file caps did not have enough reinforcement, and because it was all designed by inexperienced engineers, and the Southern Highway initial teams also did not have good experienced Sri Lankan engineers. They thought better to bring foreigners and do it, but later they learned in 2009 onwards, they learned Sri Lankan engineers are far better than foreigners. So 2013 to 2012 to 2014, Gol Matara extension was by Sri Lankan engineers. Then 2017 to 2020, Matala again by Sri Lanka. A lot of Sri Lankan engineers gave huge input, and then many other projects, even 2017 to 2021, stage 2 of Central Highway against Sri Lankan engineers, stage 1 also Sri Lankan engineers. Now it will be 2000, I think 17 to 2023. So again, Sri Lankan engineers are doing it. So when the advantage is when Sri Lankans do it, generally we don't have problems. So basically, the problem was with foreigners in this project because they have designed without understanding what they are designing, and even the local teams participated did not have enough experience. So we had now a lot of trouble. And basically, when you have a file cap, it can crack like this. In every direction it cracks and it's a huge mess. You have to do grouting and do a lot of things because delayed ettringite formation will stop after some time because once the ettringite is fully formed, it can stop its reaction. So basically, what you have to do is you have to be careful in your construction, especially when you go for high school. So if this is the problem, if this cracking is the problem, if you are not making use of any of these materials, why do you use it? Get rid of it. So how do you get rid of it? What you do is you cast your beams, 600 beam only up to 300. Place some beams on, this can be primary beam, this can be a secondary beam, and the spans can be about 3,000 to 4,000 millimeters. Place these, and on this side also you get those, and all this reinforcement will go up, and then we'll place some slabs here and do a street of 40 millimeters. The moment you do that, to make sure that nothing goes wrong, we put the whole system on props. We put props here, everywhere we put props. So the whole system is on props underneath the system part. So what is the advantage? None of these beams will have any deflection, and then once everything is hardened, so if you look at the slab system, slabs will look at, slabs will be like slabs will be like that. We precast them to 400 millimeters. 300 to 400 millimeters is possible. And then you can use Eurocode guidelines, but you have to be careful. It's not strictly applicable, so you don't have to follow all the Eurocode guidelines. So what you do is you go for testing. So basically at Morado University, we have done the testing, we have published locally and internationally. So all the data is available. So what you do is you do a normal design for BS, because these are very small members. So whether you do the design for Eurocode or BS code, no change, because they are not major members, they are minor members, because and also they are constructed step by step. So all this data is available in published form. So you can perform structural design. So when you perform structural designs, you can find that the slab can have a thickness of 50 to 55 millimeters, and then the street will have a thickness of 40 millimeters, and then we use a lot of my-steel wires for connection, because if you have any doubt of the performance of the system, you can do a load test. You can do a load test and verify the behavior, because design is there to do the calculations, but if you try a new system, and all the new systems cannot be available on the code, so what you do is when you do a new system, you do testing and prove that the system works. So these systems have been developed in 19. So these were in use in early 1990s or even before in India. And then even in 1950s, 60s, these systems are very much used in America and all over the world. Then they vanished, but the Indians continue to use them. Then we also did a lot of research. And by year 2000, the Sri Lankan systems were all developed. And now it's up to you to adopt it, because we never had the opportunity to adopt those in the last 20 years. The reason is other materials are so cheap and people are not interested. But today we have developed the system to great extent. And what we do is we actually bury a small piece of timber when you are casting the beam, and then what we do is we fix a timber piece here, a piece here, and then we place the slab panels here, the beams. So slab canals can span up to about 1.82 meters. And what we do is we put props, because now the slab panel might not be strong enough. We put props here, props here. So then we put another 40 millimeter concrete. So overall thickness is 90 millimeters. So a slab thickness 150 to 200, we bring it down to 90 millimeters. And when you bring it down to 90 millimeters, what happens? We are using only about 65% concrete. We are using only about, say, 50% steel. And we are using only about 30% formwork. And with all these things, we can say the cost comes down to about 50 to 60%. But the actual cost saving will depend on the relative prices, and then we have labor. And what we do is we actually go one step and go for high strength materials, because with high strength we can make them super thin. The reason is the cover required to protect the reinforcement will go down as we go for high strength. So that's why we go with Eurocode guidelines. Otherwise, no need to use Eurocode. We can use British code, but Eurocode is very specific with the guidelines. So you can use something like 45 to 50 megapascal concrete, or you can even go for 60 to 70 megapascal concrete. Now we have a big problem. How to get this kind of concrete at site? Because I told you, now in near future, with this very high diesel cost, you have the batching plant here, you have the site here, and there's a road that takes 1 to 2 hours. 2 hours to come, long distance, 20-30 kilometers, and these are big vehicles, heavy vehicles, so they give only about 2 kilometers per liter. And with diesel at around 500 rupees per liter, 2 liters per kilogram means very expensive. So what is the solution? Solution is this. If you want concrete, we need cement, sand, aggregates, as a metal, water. And our equation is, if you want 30 megapascal concrete, 30 multiplied by 10 plus 50, and the weight density is 2,500 kilograms per meter cubed, and the water is 200 kilograms per meter cubed. So the addition of aggregate, all the aggregates will be 2,500 minus 200 minus 350, and that will be 1950. And generally, coarse divided by sand as a ratio 1.5 to 1.8. So if you are not pumping, we can go for 1.8. So if we are not pumping, we can go for 1.8. So 1,950 divided by 2.8 gives you a value of 1950 divided by 2.8 gives a value of 700 kilograms of sand. So here you get 700 kilograms, 1950 minus 700, you get 150 kilograms of. So you make a mix like this. So this will definitely give you 30 megapascal. But how can we improve it? Yes, we can improve it. Rather than using 350, we can bring it down to about 325. And then what is other ingredient that we cannot change? This 2,500, this wet density, it remains the same. Whatever we do, this 2,500 will remain the same. Wet density cannot be changed, but we can reduce the cement content to 325, and this can have about 15% fly ash. Why we need fly ash? We like the reaction to continue. And then we have, and what can we do at the site? Can we, rather than using 200 kilograms of water, can we reduce it to 140 kilograms? Yes, it's possible. So how do you do that? We use an admixture. So now the numbers become 2500 minus 325 minus 140, 2035 divided by 2.8. So the numbers now become 725 sand plus 2500 minus 140 minus 325 minus 725. So you get 1310. So we have a new mix. Number 9. So this is 325 cement, and we have 725 sand, 1310, and water 140. Finally, when you add all, you get 2500. That is the wet density. So this has 15% fly ash. So it has about 325 multiplied by 0.15. So it has about 50 kilograms of fly ash, which is a waste product. So we get only about cement of only 275. What is the advantage? And there's a paper, research paper, you type MTR Jayasinghe DEF on web or Google search, not on the web, Google search. You type it on the Google search and download the paper on Engineer Journal. And if you look at the charts available, 275 kilograms per meter cube, cement will not cause DEF. Delayed ethnicite formation cannot be caused by this kind of low content of cement. 275 cannot cause DEF. But if it is 300 or 325, there can be slight chance. If it is 350, 375, very high chance. So how can we improve sand? We can use river sand, manufactured sand, and quarry dust. So we can use 200 kilograms of river sand because it's very expensive. We can use about 300 kilograms of manufactured sand, that is cheaper. And we can also use something like 125 kilograms of quarry dust. And quarry dust also can help in gaining strength because there can be some reaction. And then coarse aggregates, we can have chips. We have 10 millimeter, we have 20 millimeter. So we use something like 600 kilograms of this, 500 kilograms of this, and 210 kilograms of chips. What will happen? Now we are improving the ingredients, and we improve the ingredients, but we reduce one thing. What is that? That is our enemy. Who is our enemy? Water. What is the enemy of concrete? Because water creates all these bubbles in concrete and it kills the durability of concrete. So our enemy is water. So we reduce the water as much as possible by using a good admixture. But the advantage is site here, concrete here. What happens? All this journey, we lose the slump. But here when we make concrete at the site, no need to worry about slumpless, no slump loss. Why? Because we mix concrete, we place concrete. We have no time lag. It's only 5-10 minutes time lag. And within 5-10 minutes, these admixtures will be super active. So even a dry mix can be vibrated and made a super strong, super compacted concrete. And because the admixture is so active, so with 325 kilograms of per meter cube. When you reduce the water as much as possible, what is the strength gain? Strength gain curve. And you will find that the strength is gaining like this, and 28 days, what do you hit? You might hit 50 megapascal. Why? Because we have removed the enemy. Who is enemy? Enemy is water. So the problem is when you go for the modern construction practice where you rely a lot on batching plants, this cannot be done. So now I'm telling you, you can do this. Then there's a question. You can't do batching because we don't have a way batching possible. But we look at the density. What is the density? The bulk density of this is 1,700 kilograms per meter cube. This is also about 1,700 kilograms per meter cube. This can be about, this is also about 1,700. So sand is about 1,500 to 1,600. And cement is also about, bulk density is about 1,700 range. So when you know the bulk density, can't you convert it to volume? Yes, will you? But so for every material, we created separate batching box. So because we know the volume, we can easily do volume batching, and by doing volume batching, we can instead of actually it's batching, but we convert it to volume batching. So by using the bulk density, we convert it to volume batching, and with the volume batching, we get all this done. So basically, what we do is we have a system which is lightweight, which is which needs only 65% of concrete, steel, formwork. Cost has a drastic reduction, going up to about 40 to 45%. But still, the story is not over. The story is not over. So what we do is we go to next step. What is that? We have a structure that is, we have two structures, conventional and new. So this is about 20-story building. This is also 20-story building. You'll find this needs piles because its weight is 100%. The weight of this one is 65%. You might do a cellular raft with the basement, and you might save a lot of money because all this excavated soil also can be sold. Soil is very expensive these days, and all this soil that you excavate to have a weight compensated raft can be sold, and that can be used to generate money for the basement construction. So we might get a free basement, and to make it very super efficient, we go for a cellular raft. We design a cellular raft. So we excavate cement, soil, and then we replace it with the hollow structure. So you'll find now we are balancing the weight of the structure in a big way. Because the weight is balanced, you'll find the raft can be designed, and we teach our students how to do that. And I think under Civil Engineering Sectional Committee also, I conducted one lecture. It's all available on web, and there are so many. So you can type advanced computer modeling of structures. That's one of my YouTube channels. I am running 4 YouTube channels for the benefit of others. You spend a lot of my money. Everybody thinks when you run a YouTube channel, you get money. So far I have spent about 600,000 rupees or more to run 4 YouTube channels. And because I can share my knowledge with others when I run a YouTube channel. So this is the YouTube channel. And if you want, you can type my name also. then you can reach all 4 YouTube channels. There are you get a lot of very useful videos on that channel. Watch it if you have free time, and if you don't have free time, get up half an hour early and create free time. Then you can improve your knowledge and ability to do things. And then sometimes you will find now absolutely no need when you have the cellular rafts, everything, the building is up. You can go for short 3 meter by 3 meter type, huge friction pipes. This is something that we have developed recently. So instead of pile foundation, you go for a friction pile, where the friction pile is constructed by using ABC with 12% cement. And what you do is, so you can have all these structures, and then you bury the structure underneath, and then you go for a pile raft, and pile raft works only with friction piles. So how do you make friction piles? Is by using the JCB, large JCB, we excavate piles like that. Unfortunately, you can't get a positive connection. So what we do is, when you are casting, you cast columns like this, where the reinforcement is properly anchored, and this is projecting out. So we bury these odd-shaped structures, something like that. We create odd-shaped structures with reinforcement, and we bury that in the concrete ABC, so that we can have a positive contact between the raft, the piles, and the raft. All will have a positive contact, because now something buried in the pile is projecting out the reinforcement. So you can have a positive connection between the ABC based pile, the pile. Convert it to data. Just one moment. Yes, now it's on. Yes, it's automatic. Can you see the video again?
Yeah, I can.
Yeah. Okay. So basically, right. So basically, you can have structures at 40 to 45% cost of what we had earlier. So that's why I said we have 2018, 2019 projects of 20-story buildings planned for at say 12,000 rupees, 120,000 rupees per square meter. Today it has gone up to about 200,000 rupees per square meter. With this kind of value engineering, we bring it down to again 100,000 range. The moment you bring it down to 100,000 range, you can see the advantage. Advantage is now banks will find the client will find his money has not gone up. If his money is in rupees, it has not gone up. So he has this amount of rupees. Bank is willing to give this amount. In 2018, 2019, when you are talking to the banks, and today in the traditional way, you need this amount of money, banks will need this amount of money, not coming. So you say, okay, I have a new technology, I have done value engineering, and this is the cost. It's less. So bank also needs to give less. The moment you do that, okay, the projects can be kick-started, because no need to wait for any other extra money, because with the available money now we can start the projects. So all the projects that have been either not started or partially done, all can be subjected to these value engineering solutions. An engineer should not say, I'm not having jobs, I want to go abroad, I don't know what to do. Don't say all that, because even in UK, USA, Australia, Canada, New Zealand, all those countries, they are also having some trouble. And only place where you don't have trouble is Middle East, much, because they are getting more money now, because the oil prices are good. So all cannot go to Middle East. So we also have to think of our own country. So we must have solutions, are proper policies. And I told you why this 20 liters for cars, 4 liters for 3-wheelers is going to fail very soon. This is a wrong policy. We are not helping the people whom we should be helping this time. We are helping the rich, we are not helping the poor. So the system will collapse. Number 2. Then we have to think of labor intensive. And you can see now all these precast products have to be manufactured by labor. Labor will manufacture precast, and they will manufacture the building at site. And these are small members that can be cast by people. When you have a tower crane, you can move all that, and you have to fix them. You have to do all the operations at the site. But generally, up to 2022, what is our system? Fast. Everything is fast. You fix the rainfall formwork fast, you fix the reinforcement, do the concreting fast. Now, slow, but continuous. You will have 2 gangs of forming concrete. In the morning, they will precast. In the evening, another gang will come and connect. They will connect and get things moving during the night time, because nighttime concreting is very good for connecting. Daytime concreting is very, very good for precast. So precast daytime, connection nighttime. But very slow, but continuous. Everybody is working round the clock. And no noise, because we are just mixing a little bit of concrete and placing them. So you can keep the noise level between less than 50 decibels even during night. And the moment you do that, you can cover the mix a little bit so that the noise can be contained, and you can easily have a system where the construction can go on 24 hours with 3 labor shifts. And that way we can kickstart the construction industry. And then we also need training online. For whom? All these 3-wheeler drivers. And we must tell them, you are not going to be called masons, carpenters. You will be called builders, fabricators, plumbers, electricians. So we are going to call them builders, fabricators, plumbers, electricians. They will like it. And we say, earn extra with your 3-wheeler, but learn a trade. Learn a trade. For that, we'll need the something like this Australian system, what we call they call it TAFE, that is technical and further education. Technical and further education. So we need that kind of system, and we must get these people to be trades, to be masters of at least one trade or more than one trade. We can allow them to take more than one course, and we should give them national NVQ ranking of 2, 3, 4. The moment you do that, part of them will also go abroad. Then the pressure on us will be less, and we have to always think of generating employment in this at this moment if we want to come out of the mess. So with that, I'll conclude the lecture. Engineer Kamala.
Thank you, Professor.
Yes,
During this prevailing situation of the country, Engineer Professor Tishan Jaisingha webinar on the current crisis and latest technology-based solutions was very informative and excellent. Now we spent nearly 2 hours gather valuable knowledge to our day-to-day life and our engineering life. So we have to conclude this event, and I invite to Chairman of Sri Lanka Association of Institution of Civil Engineers UK, Engineer KPI Dharanpala, to deliver the vote of thanks. It's time for you now.
Thank you, Engineer Pragit. First of all, I have to say a big thanks to Professor MTR Jayasinghe, Tishan Jayasinghe, for accepting our invitation. When I called him and asked whether, Professor, can you help us in giving a lecture to for these members of the CESC, Sri Lanka Association of Institute of Civil Engineers UK, without any hesitation, you accepted that invitation.
Thank you.
So I really admire your valuable lecture. Very informative and timely, and this is your topic, the current crisis and latest technology-based solutions. You started with all conventional type wattle and dome construction, and then you explain how it converted into brickworks, and then what do you call ramp earth constructions, then lightweight concrete, then comparison of cost, time. Very informative and very useful for young engineers. And at last, you talked about this high-rise building construction and their value engineering part. So I think very, very useful. So once again, I thank you for your sharing your knowledge, and you
Thank you.
you gave some this what do you call your YouTube and other Google addresses to further improve or enhance our knowledge. So thank you very much. And secondly, I thank you. I want to express my thanks to Civil Engineering Sectional Committee of the IESL. Again, Chairman, Professor, but I think Engineer Kamala Gunawardana actively took part in this event. And
actually, Mr. Dharanpala, the Civil Sectional Committee is run by them, not by me.
But I think you are officially you are the chairman.
Yeah, but
yeah,
I
run by
have a
them.
very good team. Very good team.
Yeah,
the whole team is working very hard.
Yeah, that should be the way. I think
yeah.
I really appreciate that also. In Sinhala we say badagan nathuwa bedaganna.
Yeah, that's right.
So you have distributed all your duties to these engineers. So she and this publicity division of IESL, they supported us to conduct this event in a very successful manner. Then our present acting president and president-elect, who was the immediate past chairman of SLACE, and the executive secretary and the other CEO, who gave approval and other things, necessary things to do this flyers and everything. So my sincere thanks to them also. Then our secretary of SLACE, Engineer Pragit, you have coordinated this event with your day-to-day work also. Then I take this opportunity to thank all participants. If you are not there, so no point of having this kind of seminar, webinar. So all participants, there were about 35 participants. So I thank you also. So if I miss anybody inadvertently, I apologize for that. So I conclude my vote of thanks. So good night. Have a pleasant evening. Thank you very much.
Thank you very much. Thank you.
Thank you. Good night, everybody.
Good night. Good night.
Good night.
Good night.